Recording's re-rolling, and yeah, let's go through. All right, so yeah, you guys have probably seen all these posters or most of these posters that I'm going to go through, hang around my walls as I've been teaching them to my other classes. Hopefully, you've been looking at them, thinking about them a little bit, and then I'll go over them with you guys here. So my other classes, we started off in January with thermodynamics and heat transfer. So, like, how do you measure temperature? Well, here's three scales that are used on this planet. In chronological order, they were developed Fahrenheit first, then Celsius, then Kelvin. Now, Kelvin is an absolute scale. So there is such a thing as absolute zero. Like you can lower the temperature to a point, and then there's no such thing as like below any of these temperatures. These are lined side by side. So negative 273 degrees Celsius is what's called absolute zero. That's also about negative 460 degrees Fahrenheit. Right? So you can't go beneath that temperature. Now, for some equation applications of temperature, you have to use the Kelvin scale because the fact that it's an absolute scale, say like you scale up temperature by a factor of 2, right? Well, what is like 10 degrees Celsius times 2? Is that 20 degrees Celsius? No, you have to like multiply the entire temperature by 2, which is like much higher temperature. But in Kelvin, if you have like 200 Kelvin and you double that, that would be 400 Kelvin, right? So the Kelvin scale, you actually can scale up and down like that by some factor, some multiple. Right? Now, yeah, there's more to this, more history. I'm skipping a lot of stuff. There's what's called a kinetic energy theory of temperature, like what makes something some temperature. So this theory has to do with like how fast atoms are vibrating, right? And if they like lose all vibration, then that goes to like 0 Kelvin, call that absolute zero. Right? Here's a couple of conversion equations that's good to know. For example, the temperature in Kelvin is equal to the temperature in Celsius plus 273. So if you have like 10 degrees Celsius, you say 10 plus 273, that's like 283 Kelvin. Right? Also, you never say degrees Kelvin, you just say Kelvin. Right? Notice that there's no scaling factor here. So a change in 1 degree Celsius, same thing as change in 1 Kelvin. Okay. Right, here's how you go from Fahrenheit to Celsius or Celsius to Fahrenheit. Let's say you guys are vacationing in a foreign country and they say like, oh, it's a jolly 22 degrees outside. You're like, what? That okay, because 22 degrees might be like temperate, but you know, how do you know? Take 22 degrees, multiply by 9/5, add 32. That's the temperature in Fahrenheit, which since we in the States grew up Fahrenheit, that probably more click with our brains. Right? Here's a rough estimate. Guys, 9/5, is that really close to 2? Maybe 2 overestimates a little bit. 32, is that maybe close to 30? But that would underestimate a little bit. If you times 2 plus 30, then that gets you pretty close, not exactly pretty close, right? And if you sort of do an algebra rearrangement, you could go the other way too, right? Laws of thermodynamics. There are these basic 4 laws. The 0th law says if 2 systems are in thermal equilibrium with the third system, they must be in thermal equilibrium with each other. So if they're in the same temperature, if they're all the same temperature as each other, there's going to be no heat transfer. Okay? Why would something transfer heat? If you touch something that's hot or if you touch something that's cold, that's because there's heat energy either transferring from that object to you or from you to that object. Okay? But if everything's the same temperature, there's no heat transfer. Okay? The first law of thermo is actually one that you guys have probably applied just yesterday, conservation of energy. Now, this applies to thermal energy just like it does to mechanical energy. So if you have a closed system, the total quantity of energy in that system has to stay the same. Now, you guys deal with mechanical energy in AP, so like kinetic, potential, spring, that sort of stuff. Right? When you bring in thermodynamics, you can also bring in thermal energy. And so there could be like a temperature change caused by like some transfer of heat energy, right? But the energy is still conserved. Now, the second law, this one is a pretty important law, but gets a little bit abstract. It has to do with the time order of processes. See, like there's this question: how do you know that time is like moving forward? Like we all experience time moving forward, but you know, if you start to think deeply about that, it's like, right? Like, what's like cause effect? You know, what's sort of the physical evidence of this? Right. So processes tend to move toward more disorder. Things are going to spontaneously order themselves is one way to think about it. There's actually here. Let me switch ahead a few slides. Here we go. Right. So I skipped a few slides here. So S is like entropy. Delta S is like a change in entropy. Let's say you got 2 systems, one hot, one cold, and you put them in contact with each other. Is the cold one going to warm up and the hot one's going to cool down until they reach an equilibrium? Right. Now, so they'll each experience a temperature change. There'll be some energy change. That's what delta Q is, a transfer of energy. If you divide by the temperature that's happening at, they'll tell you the change in entropy. Now, one's gaining entropy, one's losing entropy. But if you add those entropy changes together, it's always a positive value. Right? So that tells you if you put something hot next to something cold, it will always reach an equilibrium temperature. And one way to quantify that is to say that the entropy of the system will always increase. Right? Now, even if the entropy of some object decreases, something else has to increase so that it outweighs it. Right? I've got an example of a sandcastle. It's sometimes used. It's kind of a macro example of this. If you start out with a nicely ordered sandcastle, you come back the next day and it's a random pile of sand. To where? Here. How long are you gonna be there? Okay. Yeah. So would you ever expect a random pile of sand to turn spontaneously into a nicely ordered sandcastle? No, because there are many ways for the sand to be disordered, but only a few ways for it to be ordered. Right? Similar thing with temperature. If you start off with something cold and something warm next to each other, you wouldn't expect the cold one to get even colder and the warm one to get even warmer spontaneously. Now, you can force that to happen with what refrigeration is, but it's not going to be a spontaneous process, right? So you can't. Okay, so the second law of thermo is really a statistical type law. The third law, I don't come across this one too often in like application tech, or at least that I've seen like application questions. Systems entropy approaches a constant value as the temperature first stops at zero. I don't emphasize that one too much in my classes, but right. So the first and second laws are pretty important. Right. The first law you guys are pretty familiar with. The second law is kind of abstract, but there are certain thermodynamic cycles. No, I've got a couple up here. These aren't the only ones, but these are a couple of like classic ones. Right. So what's called Carnot cycle, which tends to be efficient. So if you look at pressure versus volume, right? Here, do you guys see like a cold sink and a hot sink, right? Okay, so there might be some kind of energy transfer, and that would be like expanding some gas and like causing mechanical push, and then that when it expands, it's going to cool, so it's going to contract, and this could like cycle, right? So I got a pressure versus volume graph. Here's like the cold sink here. Here's the hot sink here, right? And then it'll like cycle around. Here's your cycle. This second graph says temperature versus entropy, right? It goes into a loop like that. Right? Here's a different cycle called Rankine cycle. This is how most electricity is generated. And so most electricity, what you do is you boil water. Now, how do you boil water? Well, you can boil water with coal. You can boil water with natural gas. You can boil water by running a nuclear reaction with uranium, right? Those are three ways to boil water, right? That water turns into steam, turns a turbine. Now, turning a turbine, it actually expends some energy doing that. It turns back to mechanical energy. So then that steam, now depleted of its useful energy, goes into this condenser and gets pumped back around, and the whole process cycles around, right? Temperature versus entropy, the area under that curve, thank you, would be the work that you do. Thanks. The work that you get, say, the energy that you put onto the grid. Okay. Stirling engine. Okay, so hot sink, cold sink, and this could cycle. Here, let me flip my. Actually, here, I'm just gonna. If you're watching the video, then you'll see the small version of this. I have a Stirling engine right here, right? I don't have the materials for this, but if I put a cup of hot water underneath this, then what it'll do is it'll expand this gas here, so this will lift, right? And then it'll start cycling this, and this will spin. So see, there's two different temperatures going on. I'll have the hot cup of water down below, and then the room temperature is relatively colder. You could call that like the cold sink, right? And then since there will be a transfer of heat energy that goes through this, so it'll convert it to mechanical energy, right? And it'll make this thing spin, right? This is a Stirling engine right here, right? Okay, so let's flip back over to PowerPoint. Stirling engine. Got here. All right, and then there's there's some diagrams to go with that. Some graphs. All right. All right. So what is the efficiency of an engine? Right. And I've got two perspectives on this. Right? So the general equation for efficiency. Now this is Greek letter eta. Looks like an N with an elongated tail. Right. Is well. Okay. So suppose you have now this is a heat engine. Right. So you got two different temperatures and it's causing something to maybe the engine, maybe a Stirling engine, for example, to operate. Right. Well, how much mechanical work are you actually getting out of that? You can quantify that in joules. Right. And what was the thermal heat transfer to start with? You could quantify that in joules. Right. Take the ratio, right, and that'll tell you what the efficiency is, and that efficiency is going to be less than 100%. Right. I guess it could theoretically go up to 100%, but only if this cold sink is like at 0 Kelvin, right? Absolute zero. Okay. Now for a Carnot cycle, which is, I want to say that's like the most efficient heat engine cycle you can have. You could do, say, 1 minus the ratio of temperatures of cold sink to hot sink. Right? So if your cold sink is like at 10 Kelvin, your hot sink is like 300 Kelvin, right? Take that ratio. Now 1 minus that. So you get something like 0.9 or 0.8 or 0.7, right? And if it's 0.7, that means 70%, like 70% efficient. You guys get that? Okay. Okay, so I went over this with you guys. Entropy. Okay. Pressure, temperature, phase diagram for water. Now, water is a nice material to work with. In fact, that you can commonly see it in its main 3 states of matter, right? Solid, liquid, and gas, right? You guys probably have a good idea what those are. Now, all of us right now are stuck at 1 atmosphere. We're at sea level. I guess if you go to the mountains, that could decrease a little bit, but basically, right? So how do you boil water? How do you freeze water? Well, the way our brains know it, because just from life experience, is you boil water by heating it. That turns it from a liquid to a gas. That's like going from left to right here, right? And you freeze it by throwing it in the freezer, cooling it down. Right? It's like going right to left, right? Left to right, right to left, right? Boil, freeze, right? But do you guys see a different way that you could also freeze water without changing the temperature necessarily? You could change the what? Pressure. Do you know what happens if you put water in a vacuum chamber? It does boil. It does boil, right? It turns into a gas, it boils. And actually that boiling process releases energy from inside that water itself, so which makes it colder. So actually, by decreasing the pressure, putting in a vacuum chamber, it boils, but it actually freezes in turn. So if you touch that boiling water, actually you would feel it getting colder and colder and colder. It wouldn't be hot at all, even though it would be boiling. There's such thing as a triple point. Where solid, liquid, and gas can exist all at the same time, but it's really hard to hit. It's like trying to balance a baseball on top of a pencil, right? It's like not super stable. Right? But you see that too. Okay. By the way, if you want to see more extensive lectures and demos and examples of all these, you guys know I posted Google Classroom all these videos for my honors classes and stuff. So you probably find the code. I think it's on my door out there, the classroom code. If you want to see this. A heat curve for water. Now this is at 1 atmosphere of pressure. Right. So suppose you pull an ice cube out of the freezer, right? And then you throw it on the stove. It's going to warm up, and then it starts to melt. Now, during that melting process, when it's going from a solid to a liquid, it doesn't actually change temperature. It stays stuck at 0 degrees Celsius. If you have 0 degrees Celsius, if you have a glass of ice water, that ice water is at 0 degrees Celsius. If it's mostly ice, then it's far left here. If it's mostly water and a little bit of ice left, it's mostly far to the right. That just tells you how much heat energy is contained inside that material, but it's all going to be 0 degrees Celsius. Now, once it's all liquid, then it starts to warm up again. They'll happen at a linear rate, so the temperature compared to the heat that you put into it, until finally it starts to boil. Now, when it boils, again, assuming constant pressure, right? So it's not a pressure cooker or anything like that. It's just open to the atmosphere. Right? Again, the temperature gets stuck, and in this case, it gets stuck at 100 degrees Celsius for sea level, right? For 1 atmosphere. Right? Now, once it's all boiled away and turned into steam, if you could somehow keep heating that steam's allowed to go above 100 degrees Celsius. That's okay. Okay. You guys can see that? Right? And there's some numbers attached to that. This line has a slope, and the reciprocal of that slope tells you like how much energy per unit mass and temperature. Right? The reciprocal of the slope is called specific heat capacity, and water has a very large specific heat capacity. What that means is that this slope is relatively shallow compared to other materials. It's really hard to change the temperature of water. You can dump lots and lots of energy in water. It takes forever to heat up. Say you put a pot of water on the stove. Guys, does the metal pot itself get hot really fast? Yeah, but that water, it might take several minutes to bring it up to boil, right? Now, once water is hot, it also takes forever for it to cool down, right? Like metals will cool down pretty fast. The water takes forever. It's really hard to change the temperature of water because water has really high heat capacity. Here's the temperature of heat, specific heat capacities for different materials. So liquid water, you guys see 4.18 kilojoule per kilogram Kelvin. That's larger than any of these other numbers, well, other than hydrogen and gas, I guess, right? Okay, Newton's law of cooling. So one thing Newton was interested in was, well, what's the rate that something will cool down? Right? So here I've got rate of heat transfer, delta Q over delta T. That's like a rate of heat transfer. Right? That depends on the material that you're working with. Say like water has some heat transfer coefficient. How about the surface area that's exposed? So you have like a cup of hot water and it's just emanating heat all day and you have a thermometer stuck in it. Right? There was an initial temperature here, and eventually that temperature is going to reach the environmental temperature. You call that room temperature, right? It might take a few hours or something, right? Right. So the rate that happens, right? Think of it sort of like the slope of the sine. You could sort of think of it that way. Right? It's related to that. Right? Has to do with the difference in temperatures, right? If it's a great difference in temperature, the rate happens faster. Right? Greater surface area, that transfer happens faster. Okay, right? States of matter. Your main three are solid, liquid, and gas. You guys probably have a good idea what those properties are. Like solids might be something rigid. Liquids can change their shape, but not really their volume. Gases can change their shape and their volume. Right? If you keep hitting a gas, you eventually ionize it. That's called a plasma. Right? And if you keep hitting that, you can get something called a quark-gluon plasma, right? Where you like dissociate the nuclei. Right? But what if you go the other way? If you cool a solid near absolute zero, it actually undergoes a really weird process where the atom sort of like collapses on itself and becomes like a wave type function. Right? It's called Bose-Einstein condensate. That's fun. Right? Density, mass per unit volume. So if you want to know like what is some material made out of, suppose here's an example I know. Let's say you find a rock, you think, ooh, I think this might be like a meteoroid or something like that just like landed on the surface of Earth. Or forget those technical details, but you think this came from space. It was, right? Well, let's see. I would know what it would be made out of, maybe like iron or whatever you suspect it would be made out of. So if I could know if this was mostly made out of iron, then maybe that could be evidence for that, right? So how would you know? It's a weird, funky shape. Well, a common thing to do is to dunk it in water, watch the volume change. That tells you the volume of that object. Now you have the volume. Throw that object on a scale. Now you have the mass. Take the ratio, you have the density. Now you can compare that to the density of, for example, iron, which is a known value. You can kind of know that. Ideal gas law. Pressure times volume equals number of moles of gas times, a constant that depends on what units you're working with, times the absolute temperature. Now, this one, it's important that you're working in Kelvin specifically, because if you like double the temperature, okay, well, you have to use Kelvin, right? You can't use a relative scale like Celsius or Fahrenheit. Right? You guys get that? Now, let's sort of think how this works. Let's run an example. Let's say you take this balloon right here, which is tied off, and you squeeze the sides of the balloon so you decrease the volume. Right? Now, the number of moles of gas, that can't change because the balloon's tied off. R is just a constant, so that doesn't change either. The temperature, I don't know, maybe the temperature fluctuates a little bit. Let's say it negligibly so the temperature doesn't really change. So we just decreased the volume, right? Guess what had to happen to the pressure at the same time? Had to go up. The pressure had to go up. You guys see there's an inverse relationship between pressure and volume? Okay, so you play around with this. Did you guys do this in chemistry at all? Chemistry? Yeah, you guys did? Okay, I always ask students. It's like some of them have seen this in chemistry, some haven't. I learned this in chemistry, so I don't know. Here, there it is. Ideal gas law. Archimedes principle. Ooh, you guys know if you jump in a swimming pool, you'll float, right? So there's like some buoyant force. There's an upward buoyant force. What is the value of that buoyant force? Right? Well, here, you can do this experiment where let's say you hang a weight. I don't know, maybe it's like 10 Newton, like 1 kilogram weighs 10 Newtons, right? And you dunk it in water. Now that scale rating goes down to only 7 Newtons. Well, that means there must be 3 Newtons of support force from the water, right? And that support force, you can quantify it, the magnitude like this. What's the, it ends up being the weight of the displaced fluid. In this case, the weight of displaced water, if this is water, right? So like if you captured all that water that ran off into a cup, that would be 3 Newtons of water, right? Worth of weight. And you could break down that formula and say buoyant force is equal to, now here's the weight of displaced water, right? The density times volume of that fluid, that represents the mass of the fluid, right, times the gravity field of the planet, right? That's the same thing, right? Now, another question though, why does the buoyant force push you up? Why does it help you float? Well, that has to do with, I don't think I made a post for this, but I'll go ahead and tell you guys. The pressure is greater the deeper you go. You guys know if you dive into a swimming pool, the deeper you go, you feel that pressure going up, right? So it's actually, that pressure is directly proportional to your depth. It goes rho g h, where h is your depth. So the fact that objects are 3-dimensional means that there's more pressure on the bottom than there is on the top, which overall creates a net force upward. Right? That's why the buoyant force pushes you upward. And then this right here is the magnitude of that buoyant force. Okay, you guys got that? Pascal's principle. So do you think I'm showing here what's called a hydraulic lift, right? You can get a mechanical advantage from this. You guys think this hydraulic fluid here has the same pressure everywhere? Yeah, same pressure everywhere. That's called Pascal's principle. Pressure is transmitted undiminished, just sometimes one way to say it. Well, hold on a minute, guys. If you pump at your bike tires, you guys pump at your bike tires like PSI, since we have American pumps you buy from the store. Does that stand for pounds per square inch? That's some kind of force per area. Now in this class, we would use like Newton per square meter. That's the SI units, which is called Pascal, right? But that's the same everywhere. So the ratio of force to cross-sectional area is the same. So if I had this hydraulic pump that has two different cross-sectional areas, I can get two different forces for the same pressure everywhere. Is that? So a small input force on a small piston can provide a very large output force on a very large piston. You can lift something very heavy like a car, right? Hydraulic press works, is the same principle. Okay. Conservation of flow. Now this is going to lead into something called a Bernoulli principle, but one step at a time here. Suppose you have a large pipe leading into a small pipe. You could make this more extreme. What if you have like a lake leading into a straw, or a straw leading into a lake if you want to reverse this, right? Do you guys think that the water has to flow faster inside the small pipe? Yeah, it does, to maintain conservation of flow. Now we're assuming constant density, which water is basically not compressible, so you can use this bottom. I think I've only ever used the bottom one in class because water is basically not compressible, right? So water is going to speed up going through the small pipe, right? So it's the same like gallons per minute everywhere. It's the same like cubic meters per second if you want to do it that way, right? Same cubic meters per second is how it works out. Okay? Now, take that idea, you can extend it, go one more step. What about the internal pressure of the fluid? Like if this fish is swimming around inside this pipe system, or even back to this last pipe system, the fish would actually feel a pressure change. And I threw in one more example here, one more detail, which there's possibly a height change. Because you guys know if you change your height inside, or your depth inside water, you can feel a pressure change also. Here, let me ask you guys this. Suppose I have a paper and I blow over the top of the paper. Is that going to lift the paper or push down the paper? What's it going to do? Here, let's try it out. I'll do this in front of the camera. So I'm going to blow over the top of the paper. Let's see what happens. Let me see. Show hands. How many guys say if I blow over the top of the paper, it's going to vacuum it up? Who said it's going to vacuum it up? Ooh, I think my winners are there. Let's see. Let's see. It does. I blow over the top and it vacuums it up. Right. Now, why is that? Again, I'm giving you guys the crash course. I know I'm going over this way too fast, but I just want to expose you guys to these ideas. If you blow over the top, that creates a fast-moving fluid. And a fast-moving fluid, if you follow what's called Bernoulli's equation here, will actually decrease the pressure. Let's see if we can sort of get this. Let's ignore the height change for a minute. Can you guys ignore the height change for a minute just to simplify this? Because there was no height change if I'm just blowing horizontal. So there was, say, like some speed on one side, and there's, say, a faster speed on the other side, a fast-moving fluid. So at the bottom of the paper was the air was at rest. Air you could consider to be a fluid. Right? The top of the paper had a fast-moving fluid, which means this green term has a high value, and it would be in pascals. It's like these are all pressure units, right? You can actually derive this from conservation of energy. If you start with conservation of energy, energy plus mgh plus 1/2 mv squared, like different energy terms, you can divide each of those terms by volume and get exactly this. Okay, start out with just your conservation of energy that you guys learned from this class. Divide every single term by volume, and now you get in terms of pressure, and it's the same thing. Right? Okay, so back to here. Right? If this green term is now very large on the right and very small on the left, then to compensate, this pressure term, this blue term, has to be very small on the right and relatively large on the left. Hey, that's what you guys just saw that I demonstrated. So a fast-moving fluid will actually cause an internal pressure drop, less pressure. This helps explain what makes a plane fly. Why does a plane fly? Part of it has to do with the shape of the plane. So the top of the plane, there's more surface area than the bottom of the plane. Therefore, the air has to move faster over the top to maintain conservation of flow. Therefore, there's less pressure on the top of the plane than the bottom of the plane, right? That's not the only reason it makes a plane fly, but that's a big reason, right? Venturi effect, this is a specific example of Bernoulli principle. So this is just Bernoulli principle in action. If you have large pipe leading to small pipe, remember that the water has to speed up going through the small pipe, and that will cause a decrease in pressure. That creates a vacuum effect. So if you have a different fluid down here, like a gold fluid, I don't know, just maybe this is some kind of maybe it's mercury. I don't know, something that's more dense than water. Right, that's going to vacuum it up. Right, you can. This is an example of Bernoulli principle. Okay? Venturi effect. Right. I know I'm showing animations of all these, but you can find photographs of all these too. Right? Stress and strain. If you, a lot of guys I bet are going to go to engineering. I mean, if you're thinking of engineering, you probably took AP Physics, right? So I know in civil engineering, I did civil engineering. You see this graph all over the place. So this is a stress strain diagram. Stress is force per unit area. It's the same thing as pressure. It just applies to solids. Suppose you have, I don't know, maybe a concrete cylinder or a steel bar. Now here I'm showing it in tension. See the forces are pulling in tension. You could also go in compression. It's the same idea. Concrete has a huge compressive strength, but it's terrible at handling tension. Metals are really good at handling tension. Okay, so I'll come back to that later. Okay. How are we thinking of it though? Strain is the percent change in length. So if you say, well, how much does it actually change in length as a result of that pressure that you put on it, force per cross-sectional area? Right? But different materials are going to strain differently, right? That's like a material property. Right? And that ratio of stress to strain is called Young's modulus. Right? Now that's as long as it's in the elastic zone. At some point, it stops being perfectly elastic. Like if you take a paper clip, you paper clip together like two papers and pull the clip off. Doesn't the clip just go back to its normal shape? Right? But what if you take paper clip together like 100 papers and then pull the clip off? Now isn't the paper clip like permanently warped? Right? Anything beyond the yield strength, it's going to permanently warp it. Right? Okay, let's get that. But if you only go to like here and then take the stress off, it just goes back to its original shape. Okay. Okay. Okay, so there's some terms: yield strength, ultimate strength. Okay, you guys get that? Right. Here's stress as a function of strain. Here's Young's modulus. Right, here's the same thing, just break it apart a little bit. Thermal expansion. Hey, if you heat up materials, do they expand? Usually, right? There's a couple of weird exceptions, but most things you heat up, they expand. Now here I'm just doing linear expansion, although you could go in 3 dimensions. But let's say you have like a bar and you really care about how much longer it gets, right? How much longer it gets is equal to its original length times coefficient of thermal expansion times the rise in temperature, right? Okay, I-beam. These are used in construction all over the place. You usually make these out of steel. You can embed it in concrete, for example. Suppose you put a force right on the top. You put a huge weight right on the top, right in the middle. And I got a couple of supports on the ends. Does that want to bend this like a smiley face? Do you think the bottom all wants to go into tension and the top all in compression? But most of the material, like these flanges, are in the very top and the very bottom. And there's some transition point in the middle where there's no tension or compression. So you don't need as much material. That's the advantage of like an I-beam. Right. Concrete. Here's how you make concrete. These materials. Right. Now, steel reinforced concrete. This is a composite material. If you put the steel in concrete, like I told you guys a minute ago, is really good at handling compression. The metals, like steel, are really good at handling tension. Now, just by a complete miracle of the universe, these two materials happen to have basically the same coefficient of thermal expansion, which means as it heats up or cools down over the course of the day, they expand and contract together. Thank goodness, because now we can actually use this to like build floor. Right now, you guys are sitting on the second floor. Romans back in the day, thousands of years ago, they made concrete structures, but they could not make second floors because they did not have steel. They didn't know this. Right now, we can sit on the second floor because we have steel reinforced concrete. All right, so we're gonna pause that here today. I won't see you guys Monday, so sorry about that. Tuesday, do a test with you guys, and then Wednesday, I guess we'll pick up with this. At least that's the plan. All right, you guys have a great weekend.